Hello friends, good evening. So here we begin. So yesterday's one numerical, find the moment of inertia about one of the diameter of hollow sphere of mass m, inner radius and outer radius is given. I think we left it at half. So I'll just recapitulate. So if you take this as a sphere, the cross section of a sphere, so this is it. So they had given us this R and this R, and they have told the mass of this portion is M. Clear? Hello?
Yes, sir. Yes, sir.
Yes, and we would like to find the moment of inertia about this axis, say AA dash. Okay, so that's it. So now mass is given, and we need to go about doing it. What will be the strategy you would like to adopt for this?
Like we can calculate the moment of inertia of the larger radius minus smaller radius, sir. And for smaller radius, we can take the mass, like we can take mass per unit length, and then we can calculate that small mass length, which was separated. Yes, sir. Then we get the final moment of inertia.
That is, you will take the moment of inertia of a solid larger sphere.
Yes,
and the moment of inertia.
Of smaller sphere.
Yes, good.
For the mass of smaller sphere, we can use mass per unit length, and we can find out.
Yeah, so we can find it. That's right. So therefore, the if you take the inertia of this circle R to R, sorry, if you take the moment of inertia of this R to R, okay, then this will be moment of inertia of the larger one minus the moment of inertia of the smaller one. That is, we are calculating the moment of inertia of the spheres of radius r and moment of inertia of the solid sphere of radius small. Clear? I think we'll adopt this strategy.
Yes, sir.
So if you want to adopt this strategy, then for us now, IR minus IR. So this is for solid sphere, right? So
yes.
Taking solid sphere here. So for solid sphere, it is going to be 2 by 5 the mass of the bigger sphere, okay, into r square, okay, minus 2 by 5 the mass of the smaller sphere, okay, into smaller sphere. What I mean is, this is the bigger sphere, okay, of radius capital R, and then you have the smaller sphere of radius smaller. So if you take the moment of inertia of this minus the moment of inertia of this, I think we will get the answer. Correct?
Yes, sir.
But the data that they have given us is, they have told here m is equal to mr minus mr. This is the data that they have given.
Yes, sir.
Okay. So, but they have not given these two quantities. Okay. So, under these circumstances, we will have to see something which is common to both the spheres. I am sure all of us will appreciate that. It should be the density. The density should be same.
Yes, sir.
Density should be same. So therefore, we can straight away take the density here to be rho, and for this mr, so rho into the volume of this 4 by 3 pi r cube minus 4 by 3 pi r cube. So this will give us, so rho into this will give you mr, rho into this will give you this. Clear?
Yes,
Hello?
Yes, sir.
So that should make our life simple. So here I can pull out the things that are 4 by 3, rho pi is common. So I get here r cube minus r cube. I get this. Okay, but still, I have instead of two unknown variables m capital R, m suffix small r, I have ended up with density. Hello.
Yes, sir.
I have ended up with density. Anyways, let's see how to ward off that and get going with this. Right? Okay, can you take it over from here and solve it?
Yes, sir.
Huh?
Yes, I have done, sir.
You have done it. Okay, fine. What about others? Did you do by the same method or something different? So what will be your next step here now? So the next step here would be writing this equation here. So this will give me here 2 by 5, okay, mr minus mr. So we got mr minus mr in terms of this. So here I will get here r square is here. Hello? Hello friends?
Yes.
So
Yes,
how will you go about doing it here? So 2 by 5 is constant, and instead of mr, I'll write it as rho into 4 by 3 pi r cube. That is for this mr. Okay, into r square.
Yes.
Okay. Minus 4 by 3 pi small r cube for the smaller r into small r square. Okay.
Into rows.
Into row, I have to into row. So I'll do one thing. I'll put the row outside.
Yes.
I'll put the row outside here. In fact, I can put the other things also outside here. So 2 rho by 5 into 4 pi by 3. That also I can pull it out. So I get here r raised to 5 minus r small r raised to 5. So this is it. Now, yes, fine. So from this I can substitute for rho. So I get here rho is equal to 3m by 4 pi, okay, into r cube minus r cube. Okay, so I just substitute that here. So if I substitute that here, 2 4s are 8 pi by 15 into the row. The row here will be 3m by 4 pi into r cube minus small r cube, and in this numerator I get it as r pi minus r pi.
Yes.
Right? So 3 1s are 3 5s are here, 4 5s are 4 2s are here. So I end up getting with 2m by 5 into r to the power of 5 minus small r to the power of 5 divided by r cube minus r cube. I end up with this.
Yes,
Dear friends, did you also some other? Yes, sir. Shishan, you tried. You got the same answer.
Yes, sir. It's the same answer. It's the same.
Yeah. Okay.
Yes,
I have used this method. Have you used some other method and solved it? Similar method. You have also used rho and solved it, right? Or somebody did some integration and tried to do it. Nothing like that. Nothing like that, no?
Actually, your integration will be better for me.
You like to integrate it into it. Okay, fine. So let's just see whether this answer is right, and we shall just see with integration how we can do this.
Yes, sir.
Right? Because we should be ready with the different ways of handling this, because we don't know in examinations what type of questions is asked. The more the skills we learn, then it's better for us. Okay, the answer is same. But well, this is what I don't like in these printed solutions. This is nice diagram, I suppose, But this one, you see, initially only they calculate the density, because the need for this must arise. Okay, then we should be able to do it. Anyways, we got the same answer.
Yes, sir.
Right? Huh?
Yes, sir.
Okay, fine. So if you wanted to use some other method, somebody said integration, then how do you go about doing that? Just give some idea.
Change the limits from smaller to R. So we take R first, smaller to R.
Point R to R will take. But what will be the integrand there? What will you keep it within the integration side? So that means now you would like to take something like this. That is, you take this hollow sphere of radius small r, right? And then the moment of inertia for this will be 2 by 3 into m into r square. That's what is the formula that we use here, correct? Moment of inertia of this. Did you use this and then you build it? That is, you start adding many hollow spheres. Did you do it like this?
Yes, sir. Yes, sir.
Then you see, I'll just tell you how to go about doing this. I'll just tell you. So here, if you want to use this method, then we need to consider a hollow sphere, but of thickness dr.
Yes, sir. Yeah.
Of thickness dr. Then what happens here? See, then what happens here? We will get the expression for the moment of inertia of this. Okay, or I'll say di for this. I will take this moment of inertia di is equal to 2 by 3 instead of m, again I have to use the density here. So density I will use into, sorry, not density, I will instead of the mass. See, if I take the total mass of this, if I take the mass of this as dm, okay, then dm divided by 4 pi r square. This will give you what? Mass per unit area. Hello?
Sir, we'll take volumetric mass.
You will take volumetric mass and do it? Okay, then we'll take it like this. dm by 4 by 3 pi r cube. We'll take this. R cube minus?
R cube. Like our original mass and volume were that same, sir. Rho, sir. 4 by.
And then we are doing the same formulation. No, I was thinking of, building this layer by layer. Building this layer by layer. That's what I was, planning to do. That is, if you want to take only this layer, okay, what will be the mass of this small layer that you take here? See, the volume of this thin layer, man, the volume of this thin layer of dr, the volume of, that's what. So 4 pi r square, okay, into dr. That will be the incremental volume of this. Okay, and then if you multiply it by rho, then it will give you incremental mass dm. It will give you incremental mass dm. And then for this dm, you find out the moment of inertia. So what is the moment of inertia for this dm? It will be 2 by 3 dm into r square.
Yes.
You get this. Okay. And now you have to further this. So if you want to get the total integration, then you write it here. 2 by 3 into dm, you will write it as 4 pi rho into r square into dr into this r square.
Yes, sir. Yes, sir.
Okay. And this you have to integrate it from small r to capital.
Small r to r.
Capital R.
Yes, sir. We'll get same thing.
We'll get same thing. Huh?
Yes.
But only thing is now this culprit will be again a row here. So because m is given to us, So we have to find rho, again the same thing, we'll have to find the volume anyway will be 4 by 3 pi into R cube minus R cube. This will be the volume into density. So we can substitute the density point here and then pull it out and do it. Okay, that also should give us the same answer. I suppose some of you at least understood this method.
Yes.
Building on yes, good, thank you. Fine. So that's it. Shall we proceed, student, with the next numerical?
Yes, sir. Yes, sir.
Yeah. Thank you, friends. Thank you very much. All right, great.